Hello, everyone. We'll just quickly get started. Um, okay, in this presentation, I'm going to talk through the machine learning project that I worked on as part of the course on machine learning AI in product. The goal here in the project is to predict the electrical energy output of a combined cycle power plant. Um, I'll cover how I thought about the problem, the models I tried, and based on which the comparison metrics I used to come to analyze the models and the final model which I use and the final results, a demo of the results of the model. So great, let's get into it. Um, Let me just do a slideshow mode. Should have, I think. Okay. So the data set we are here working on is about around 9,500 hourly sensor readings from the real power plant. And for each hour, we have four environmental measurements: temperature, exhaust to vacuum, ambient pressure, um, and relative humidity. You can see, then what we are trying to predict here is the net electrical output. And the unit of measurement is megawatts, MW. Um, and the output ranges anywhere from 420 to 496 megawatts. So it's a continuous number that immediately tells us that it's a regression problem, not a classification problem, because we're not trying to categorize things here. We're trying to predict a numerical value, or we're trying to get to an output and not categorize anything. So this is a regression problem. So just moving on, uh, we'll talk a little bit about the data first before jumping into the models. The first thing which stands out is it's a clean data, and how out of the four variables, how temperature has the strongest negative correlation, which basically means higher the temperature, lower um, the output. Uh, Basically, the hotter it is outside, the less electricity the plant produces, which makes sense because gas turbines are less effective, less efficient in hot air. That's something that I read online. Exhaust vacuum and had a similar strong negative relationship, around 0.87. Ambient pressure and humidity were weaker, but still meaningful, around 0.52 and 0.39 respectively. Um, and the good news here is we had no missing values, so I could use all four features without any cleaning headaches. Given that all four showed some relationship with the output, we decided to include all of them in the model. And for the modeling approach, I first, uh, and sorry, we can also see I've just put a bar graph of all the variables here and the output. I can see the mean that I've plotted here. Uh, all the input variables and the output variable, which is energy output. Um, Now let's look at the modeling approach. I've split data into two parts. One is training and test. 80% is in training, 20% in test. Um, um, then on training data, I use five-fold cross-validation on the training to set a fairly comparative model. Sorry. Uh, Metric used for comparison is RMSE, which is root mean squared error. This penalizes, as we learned in our course, it penalizes large errors. Same units as target, which is megawatts. The four models which we compared: linear regression, ridge regression, random forest and gradient boosting. Uh, I will now, yes, now these are the scatter charts which I've plotted, um, comparing each input variable versus the output that we've seen, just to understand how closely, how are these input variables related to the output, which is the energy output. So as you can see, temperature is has a very close correlation, negative though, negative correlation, but a very close correlation with the energy output. The rest are not as closely correlated. Now moving on, let's compare the models. So there are four models as we spoke about: linear, ridge, random forest, and gradient boosting. Now both the linear models, linear and ridge, they performed similarly, uh, with the mean squared error being the highest. Um, this relationship has non-linear components that I think linear models miss, and that's the reason why the root mean squared error is the highest in these two models. Now, between random forest and gradient boosting, uh, gradient boosting got down to 3.76 megawatts as a root mean squared error, and random forest was the best, which is 3.46. So random forest here, clearly outperforms all the models and is a clear winner because the lowest root mean squared error on the model. Now moving on, now that we know that random forest is our model of choice, let's look at how the model performs. Just taken samples of the model output, and we can see here clearly that and I've just used a few thresholds that if it's less than 2 megawatts, the error, if it's less than 2 megawatts, I've just colored them green. Anywhere between 2 to 4, I've colored them yellow, and red cells are more than 4 megawatts of error. The error is described as the difference between predicted and actual. Um, on most readings, you can see it's anywhere between 2 to 3 megawatts of actual output, the errors. Uh, and so this is the demo of the model. There are 5 green, which is less than 2 megawatts, 2 yellows, which is 2 to 4 megawatts of error, and 3 reds, which is more than 4 megawatts of error. And the final evaluation, we tested 1914 samples, root mean squared error of 3.25 megawatts. On these samples, the mean absolute error, MAE, was around 2.33 megawatts on average. So on average, predictions were off by 2.33 megawatts, and the R square here is 96.9637, which is a very strong R square. It explains more than 96% of the variance in the energy output. Um, and uh, yeah, one more observation was temperature was which accounts for 90% of the model's decision making. It's based on the gradient. Again, based on a gradient boosting model, the temperature stands out as the most important feature. And finally, it's just a executive summary here. We've done a regression predicting continuous energy output. Again, not a classification. Random forest are not the best across the via five-fold cross validation, with having because of having a least RMSC. And the final results were the RMSC was 3.25 megawatts. Mean absolute square error was 2.33, and the R square was 0.96. Key insight is that the temperature is the single most important predictor consistent with the physics of gas turbines. The model could realistically be used to forecast plant output and support operational planning. So thank you, everyone. This is my output of the project. Uh, Thank you.